Hello. I thought I'd go through some of the questions that you were doing in class, just so that if you found any of them difficult, you could have a look here and hopefully work out how to do these with impulse. So the first one I was going to do was number 69. So the first part says estimate the impulse, and just as a reminder, the other word for impulse is the change in momentum, and it's force times time. And because this graph is plotting force against time, that's the area under this graph. So what we need to do is find the area under the graph. Now, the easiest way to do this is to count squares. So there will be some leeway in the mark scheme, depending on how generous you are with these half squares. So I reckon that the number of squares is, I counted, when I just did this a few moments ago, I counted 62. And now you need to know what each square is worth. So let's work out what each square is. So take a square. That is 0.1 from this axis, and that is 1000. So 1000 times 0.1 is 100. So total area, in other words, the impulse, is 6,200 Newton seconds. You will get some range. It doesn't matter if that's 58 or 63 squares or 64 squares. There will be a range that you're allowed. Okay, next let's look at B. So it now says, so just before the collision, alright, so now we've got a before and after situation. So before the collision, so I'm going to sketch this out, I'll call them A and B. Before the collision, there's a faster car and a slower car. And the faster car collides with the slower car. We're not told anything about the slower car, so we can just ignore car B for the moment. So the faster car has mass 1,200 kilograms, and it was travelling at 18 meters per second that way. Okay, and the question is asking for what's its collision after. That's a bit wonky. So this is before, and what happens after. Now this is where we need to read the thing up here. It says after the collision they did not stick together, so the two cars aren't heading off in the same direction. Okay, they're not doing that. What they are doing, if they're not sticking together, is B is going to be heading off in this direction, and A, this is really important, is going to be bouncing back. Okay, probably with a lesser velocity, but we don't know. A is going to change direction. So that bit there where it says they did not stick together means that A is going to be coming back. Okay. Now again, we don't know anything about car B. All right. So what we can do for this is calculate the momentum of this beforehand. So before, the momentum of A is mass times velocity, which is 21600 meters per second. Sorry, I'm out of space. And we don't know anything about after yet. We know that its mass is still that, assuming nothing fell off. We don't know that. And we don't know this. But we do know that its change in momentum is 6,200-ish Newton seconds or kilogram meters per second. I think I'll stick with the same units all the way through, it's probably easier. Okay, so that's the change in momentum. Now this is where the direction makes a huge difference. So it was going this way with 21,600, and afterwards it's now going this way, and between here and here the change is 6,200. Okay, so what we need to do is because we know it's changed direction, its momentum has changed. So 21,600 minus 6,200 is going to equal this new momentum. So the momentum after is that. Okay, it's losing momentum because it's giving some momentum to B. The fact that it's bounced back means that we know that this momentum change has been negative. So if I stick that in my calculator, I found out that the change that gives it makes a new momentum 15,400, which is equal to mass times velocity. So we can work out the new velocity is 12.8 meters per second. Okay, so watch out with the direction and watch out for things like where it says they didn't stick together, so you know that A comes out going backwards. Okay.